Good afternoon. Can everybody hear me and see the PowerPoint slide?
Yes, I can see.
Okay, thank you. Are there any questions?
Professor, could you do a problem from exercise set 3, problem 2?
Problem 2. Let me see. Exercise set 3. Well, which one do you want?
Problem 1 would be good, or whichever is the shortest.
You mean 2A?
Yes, sorry about
that. Okay, so this is all right. Let me write this down. To make sure that everybody gets this, L is 0, I, 1 to the I greater equal to 0, union 0, I, 1, 2 to the I greater equal to 0. Okay, so in this case, the first observation here is that we want to get a PDA such that that PDA accepts by final state. Okay. Now, let's split that into two questions. The first one is this. How do we do that? Well, we have already basically done that. You have a marker. For every 0 that you see in the input, you put a marker on the stack. And you do that in a particular state. And we've done that already last time, so this is not particularly interesting. The important thing is you do that with a certain number of states. So you have Q0, which is your initial state, and in Q0, basically, you start the whole process. At this point, there's nothing that says we have to have a deterministic automaton, push-down automaton. So in Q0, well, we have zeros, and we have ones, and we have epsilon. And so in Q0, we can go to state Q1, or to state Q whatever, would probably need 3. And so we put Z1 on the stack. So this is the Z that we have. And then we put, if we go to Q1, we go to Z1. And if we go to Q3, we go to Z2. The idea here is that in Q1, we do this. In Q3, we do this. Okay? And we have, well, I'm keeping things sort of clean by having different initial stack symbols. So we basically have a stack symbol Z that starts the whole process, but we're never going to use it again. We have Z1 in order to get the first portion, and we have Z2 if we want to get the second portion. So the idea here is that we transition consuming nothing, epsilon, to Q1, and in Q1 we do 0 to the I, 1 to the I greater or equal to 0, the way we've done this last time already. Okay, and then in Q3 we do 0 to the I, 1 to the 2I, I greater or equal to 0. Okay, now if you want to be precise, then of course, because either one of those two includes epsilon, so we have a third possibility for epsilon in Q0 with stack symbol Z, where we go to QF and whatever, we can empty the stack. So that means we go to the final state, but we also empty the stack. So in this case, that takes care of the epsilon. So that means we can actually do in Q1 0 to the I, 1 to the I greater or equal to 1. And in Q3 we do 0 to the I, 1 to the 2 to the I greater or equal to 1, because the epsilon has already been taken care of with this. And so we've done that already. So this is state Q1 and Q2 where we do that. And then state Q3, now we have to do the following, and I'm not going to go into detail, but I'm explaining to you what is behind the whole scheme. You put zeros on the stack. You put a marker for each 0 on the stack. So eventually you will have a bunch of markers. Say A, you have Z2, and then you put an A on top of the stack for every 0. And now the question is, when we transition, when we see the first 1, what do we have to do? Well, we can't take an A off for every 1. That would be if we had 0s and 1s. In that case, of course, we take, for every 1 that we see, we take a marker off the stack. But in this case, where we have 0 to the I, 1 to the 2 to the I, in that case, we have to read 2 1s in order to be able to remove 1 0. So you need another state. You have, when you see the 1, you change to Q4, and you don't take anything off the stack. And then you see another 1, and you go to state 5, and at that point then you take an A off the stack, because now you have seen 2 1s, and for every 2 1s you need to take 1. You have to have a single matching 0, and so that means now that you've seen 2 1s, you're going to take 1 A off, and then you keep looping on that. Does that explain the whole principle? And then, of course, you can do the same thing with a 0 to the I, 1 to the 3I, or 1 to the 4I, or whatever. It just requires a number of states where you basically ensure that you have the correct number of ones. And when you've seen the last of that group, so in this case, the last of the pair of ones, then you'd actually take the marker off for the 0. Does that give you an idea? Anybody? Whoever asked the question?
Yes, thank you.
Okay. Any other questions? All right, so then we are going to look at well, I've indicated last time already what the program is going to be. We are going to establish that acceptance by empty stack is equivalent to acceptance by final state for push-down automata. That requires, the things are not entirely straightforward. So let's see, first point is given a push-down automaton P1. There exists a push-down automaton P2 such that n acceptance by empty stack of P2 is equal to L of P1, acceptance by final state. So L is final state, N is empty stack, just so that you remember what we did last time. So the idea is relatively straightforward. There are some tricky details that we will have to look at. So the idea in this case is once, so this is the idea, once we are in a final state, transition, move to an empty state, I call that, put it in quotes, consuming epsilon, and in that empty state the stack is cleared. So if we get to a final state in P1, then in P2 we now want to consume epsilon, meaning nothing, because obviously we don't have any other, presumably at this point the word that was presented is all consumed, every letter of the word has been consumed, and so we have consumed the entire word. and end up in a final state. And so in that case, we consume epsilon, which means it's free, and transition to that empty state. And in that empty state, well, we can call it QE. And in that empty state QE, we then clear the stack. So the entire stack is now emptied in QE. So basically, how do we achieve that? Well, we're in state QE, and we have our stack symbols Z and X and Y and so on. And for any of the letters of the input alphabet, we don't do anything. But for epsilon, we're basically going to say we are going to stay in the state QE, and we clear whatever stack symbol we see on top of the stack. So if it is Z, we clear it. If it is X, we clear it. And clearing, of course, means we replace the top stack symbol with epsilon. And QE for Y, we clear it, and so on and so forth. So for every stack symbol that exists, we are going to remove it in that new state QE. So basically, we add that state, and we, whenever we are in a final state, so if we have a QF, and there's stuff that is happening, well, using the epsilon transition, we go to QE, and we keep whatever, well, we can remove it. It doesn't make any difference. So for all stack symbols, we can again do the same thing. So this is really a one-track mind. Whatever stack symbol you see in the state, in a final state, you're going to transition, you add. So this stuff, whatever you have, and there may be stuff here, okay, under epsilon, you keep that, but you add, so this is add. Those transitions which get you to that new state QE, and in that new state then you simply clear out the stack. For every stack symbol that could possibly occur on top of the stack, you're going to remove it, and you stay in that state QE, and you keep on going until nothing is on the stack. So that is the idea. Everybody understand what the idea is? Because now I'm going to make it a little bit more confusing. The idea is a good idea, except there is one problem. So what is happening here? We are basically having that PD push down the tablet on P1, which accepts by final state. And so in order to modify P1 to obtain P2, we add these transitions to the empty state for every final state. And in that empty state, we now clear out the stack. And in that way, every word that was accepted by P1 is going to be also accepted by P2. That's no problem, because this construction will achieve that. The problem is that P1 could, in fact, at some point empty the stack. Now, if P1 happens to be doing that in a final state, then there's no problem. But the problem is, what if P1 may empty the stack not in a final state? So in that case, P1, which of course accepts by final state, would reject that word, because it's not in a final state, and P1 accepts only by final state. However, when we do that modification of P1 to get P2, it turns out that now P2 would empty the stack. And the fact that it is not in a final state, who cares? The stack is empty, and that's when P2 accepts. So the construction that I've given you here will ensure that every word that is accepted by P1 by final state is also accepted in P2 by empty stack. But it doesn't necessarily imply the other direction. In other words, there may be words that in P1 emptied the stack, but not in a final state, which of course, if we do that modification to get P2, in P2 now the stack is emptied for that word, and in contrast to P1, where that word was rejected because it didn't end up in a final state, in P2 it is now accepted because P2 accepts by empty stack. So how do we get around this problem? Well, we have to add a new stack, initial stack symbol, Z0. Okay, I'm sorry, Z0 prime. And so this is new, Z0 prime is new. And it basically now guarantees that whatever P1 did, it can mess. So we're now simulating the stack of P1. So this is the stack of P1. But P1 can only remove symbols from the stack that were in P1. And since Z0 prime is new, not in P1, Z0 prime can't be removed. Now, QE, on the other hand, will remove Z0 prime in the state QE, because it removes, QE removes everything. And as a result, it follows that with that modification, so we now have to create a new stack symbol. We basically now start with that stack symbol Z0 prime, and then we start in a new state Q0. So we have a new state Q0 prime. And Q0 prime basically then starts with Z0 prime and then puts Z0, if that is the initial stack symbol of P1, puts it on the stack. So this is now the stack of P1. And now it transitions, all using epsilon, to Q0, which is the initial state for P1. And so now P1 can merrily go along and do whatever it does on its stack, which is this portion. And finally, when we then get to the transition where I say add in the red, then we have the move from any final state QF to QE. And in QE, we are going to remove all stack symbols that were in P1, plus that new stack symbol Z0 prime, which we introduced in order to have a permanent bottom marker below, which cannot be removed by P1 because P1 doesn't know about Z0 prime. Okay? So now we have ensured not only that every word that is accepted by P1 is also accepted by P2. That was already the case before. But we've also ensured that there can't be any situation where a word in P that is accepted by P2 would not be accepted by P1, because the only way the stack can be emptied in P2 is by actually going to QE. And in QE, we're removing all the stack symbols that exist in P1, plus that newly introduced initial stack symbol Z0 prime, which didn't exist in P1, but now is this initial stack symbol of P2, and that then guarantees that the problem that we've identified, that P1 may empty the stack, not being in a final state, well, that's not going to result in P2 accepting it, because it will only empty this stack, but it will not get rid of the Z0 prime. And for that, we actually do have to transition to QE, the empty state, in P2, and in QE, then we can actually get rid of that Z0 prime, but not in any other way. And so in that case, we now have essentially established that the state, the push-down automaton P2 that we got from starting by P1 is going to accept by empty stack exactly all the words that are accepted by final state by P1. Okay. Any questions about this? No questions? Is everybody, can I get some feedback just to know that we haven't been disconnected?
I'm just going to ask, is Z0 prime part of P1 or P2?
Say that again?
Right now, Z0 prime is part of P1.
No, Z0 prime is part of P2. Z0 prime is new.
Okay.
Z0 prime is not a stack symbol of P1. This is the new initial stack symbol that we start, with which we start in P2. That's the reason why P1 can't remove Z0 prime. So this problem that I identified here, P1 may empty the stack not being in a final state. Well, it can empty its stack, but that doesn't allow it to remove Z0 prime because Z0 prime does not exist in P1. Therefore, it doesn't know it, and therefore, in particular, it can't remove it. So it can empty all that stack, which is the stack of P1, but it won't be able to empty this stack because that would require it to remove Z0 prime, and you can't do that. Okay? So with this, we have basically now solved the first question. Given a push-down automaton, P1, there exists a push-down automaton, P2, such that this new automaton, P2, accepts by empty stack exactly the language that is accepted by final state by the given push-down automaton, P1. And now, the converse. Given a push-down automaton P3, there exists a push-down automaton P4 such that, so the first time we went, the new one accepts by empty stack. Now the new one has to accept by final state. So P4 accepts by final state exactly what is accepted by empty stack by the given push-down automaton P3. And so here again we have an idea, and the idea is, and of course once again the idea is not necessarily the way it's going to work, but the idea is when the stack is empty, move to a final state consuming epsilon. So essentially the idea is we have here our stack, and when the stack is empty, then we're going to go to QF. We consume nothing. So this is using consuming epsilon. And we then accept by final state. So in this case, there is an immediate fundamental problem. How to move when the stack is empty. Obviously, that is not entirely trivial, because if you remember, the move function basically takes a state and a stack symbol and a letter from the alphabet, or epsilon, and then it does something. Well, it goes to state P, and then it replaces that top stack symbol by some string consisting of stack symbols. So P and Q are states. A is either a terminal input symbol or epsilon, and Z is a stack symbol, and gamma is a 0 or more stack symbols in gamma, capital Gamma star. So that means basically when we see, we're in state Q, and we see a stack symbol Z on top of the stack, and we're consuming an input symbol A, which could be epsilon, then a move would then consist of changing state from Q to P and replacing that Z on top of the stack by gamma. That, of course, is a problem, because if we don't have anything on the stack, in particular, there is no Z on top of the stack. If the stack is empty, then there is no way of moving. Well, by now, of course, you should have already some idea of how we're going to finesse that, because obviously we're doing this. So this is the stack of P3, which is going to be empty at some point if a word is accepted. And so now we're going to put a new stack around that with a new stack symbol Z0 prime. Okay. New Z0 prime for P4. And so that means that P3 emptying its stack exposes Z0 prime on top of the stack, because that's how we're going to simulate the stack of P3 in P4. So this is in P4. And now, of course, we have resolved this problem. There is now something on top of the stack. It's the Z0 prime, which essentially signals that the stack of P3 is empty. And so when we have a state, whatever state it is, and we have Z0 prime, and there are other states, other stack symbols which we're not interested in, we just keep whatever it was. But when we have exposed Z0 prime on top of the stack, then we're going to go to QF. And, well, we can leave the Z0 prime alone, or we could empty it. It doesn't make any difference. But the important thing is this is now the F, QF. So this is the final state. And in the final state, of course, we now accept in P4. So this transition, this move, is going to be added for Z0 prime and nothing else. So when we consume epsilon, which means we're consuming nothing. And in whatever state, this is for all states. When we expose Z0 prime on top of the stack, Z0 prime is the new stack symbol, initial stack symbol, then we can transition to QF. So that allows us to do this with the empty stack of P3, because in P4 the stack is not empty, it contains Z0 prime. So what that then means is that we have effectively shown that given any push-down automaton P3 that accepts by empty stack, we can find some other push-down automaton P4 that will accept exactly that language that the P3 accepted by empty stack. P4 then accepts by final state. So that then gets us back to what we stated here, that acceptance by empty stack is equivalent to acceptance by final state, which of course in practice means we can pick whichever mode we prefer. So in many cases it is advantageous to find an automaton that accepts in one particular mode, say by final state or by empty stack. However, you may have a construction that does it the other way around. So suppose you want to find an automaton that accepts by final state, push-down automaton that accepts by final state, but you are actually having a construction that does something you're interested in that gives you a push-down automaton that accepts by empty stack. Well, then you just throw the second construction at that automaton. You have an automaton that accepts by empty stack, but you want one that actually accepts by final state. So the construction that you had, and we will see one of those constructions, that will give you a push-down automaton that accepts by empty stack. If you don't like acceptance by empty stack, you can then, using this construction, obtain a push-down automaton that accepts that language by final state. Conversely, if you had a push-down automaton that accepts by final state, but you really don't want to accept by final state, you can always find a push-down automaton that accepts by empty stack that accepts exactly the same language as the given automaton by final state. So the two of them are equivalent, so this goes back and forth, final state, empty stack, these two are equivalent. Any questions about this? So that gives you a way of converting a push-down automaton that accepts using one mode to a push-down automaton that accepts in the other mode. So you can go from acceptance by final state to acceptance by empty stack, or you can go from acceptance by empty stack to acceptance by final state. A byproduct of that is, of course, that you can easily see that you need only a single final state if you want to accept in some language in a push-down automaton by final state. How would that happen? Well, suppose you have a push-down automaton that accepts by final state, but it has many final states. Well, you first can convert that to a push-down automaton that accepts by empty stack. And then you take that push-down automaton that accepts by empty stack, which of course accepts precisely the language that the given push-down automaton accepted by final states, more than one. And then you throw the other construction at it, where you take a single, you get basically a single final state. That QF is the only final state it has. And so that shows you that you can always get a push-down automaton that has a single final state if you want to accept by final state. Now, this is sort of a roundabout way of showing that, but it is certainly quite straightforward conceptually. You may want to stay away from the details, but certainly conceptually it's quite obvious that you can always accept. If you want to accept by final state, all you need is a single final state, and that is it.
Sir?
Yes?
It might be slightly unrelated, but are there any clues or things that we could look for that would help us develop a desire to go one way or the other with this? Or I think maybe if could it be if there's many final states we may want to go to convert it to empty stack, or?
No, if you give me another 5 minutes or 10 minutes, you will see an example where we have a construction that will yield a push-down automaton that accepts by empty stack.
Okay, but there's no general. Oh, I'm
The
sorry.
construction that I'm going to show you will give you a push-down automaton that accepts by empty stack. Now, for whatever reason, you may not want that automaton. You may want one that accepts by final state rather than by empty stack. Well, then you can apply this construction. So give me another 5 or 10 minutes, and then you'll see what I am referring to. Basically, what you're going to get is a construction of a push-down automaton for a given context-free grammar. Okay? So the next issue is context-free grammars. Context-free grammars are equivalent to push-down automaton. Now again, well, first of all, what does that mean? Given a push-down automaton, we can construct a context-free grammar, and given a context-free grammar, we can construct a push-down automaton, such that the languages involved are exactly the same. So in this particular case, we're going to look at the issue given, this is given a context-free grammar G, construct a push-down automaton P such that, well, in this particular case, this push-down automaton will accept by empty stack what the context-free grammar generates. So the language generated by the context-free grammar is going to be exactly the language accepted by the push-down automaton by empty stack. So in this particular case, given a context-free grammar G, the construction that I'm going to give you is one that gives you a push-down automaton that accepts by empty stack whatever that context-free grammar generates. Now, before we get to that, we have to do a little bit more discussion of derivations. and in particular leftmost derivations. If we have a derivation, and let's look at an evil grammar. You will see in a minute why this is an evil grammar. Now, if you look at this, obviously it has a single variable, e, which obviously is its starting symbol. It has plus, times, open paren, close paren, and id as terminals. And if you look at that, then what do you think is the language generated by that grammar? So obviously, this grammar G is fully specified by given these 1, 2, 3, 4 productions, because E is obviously the only variable, and so it must be the starting symbol, and plus, times, open paren, close paren, and ID are the 5 terminals, and so the productions are those 4. And so what is the language generated by this grammar? Anybody willing to venture a guess? Multiplying or adding IDs, yes, but can we go a little bit further? I claim that this language consists precisely of all possible arithmetic expressions involving addition and multiplication. Polynomial? What? Hold on. No, there's no polynomial IDs. All arithmetic expressions involving plus and times. So, for example, we may have E goes to E plus E, and then we have A, and then we have E times E, and that goes B, and that goes C, so this would be A plus B times C. And so if we write that as a derivation, then we would have E derives E plus E, and then that derives A plus E, and that derives A plus E times E, and that derives A plus B times E, and finally that derives A plus B times C. And so this is clearly what we have. This derivation 3 is essentially equivalent to this derivation. Now, this derivation has a particular property, and that is that it always uses the leftmost variable to do the next derivation. So we have, obviously, the first step is trivial. There is only one variable, and so we are messing with that, and so LM stands for leftmost, so that gives us E plus E vacuously. And then this is, in fact, not trivial anymore. We're going to replace the first variable, e, by e goes to id. All right? And so we have a plus e, and then the next one is again trivial. There is only one variable, so we're going to mess with it. And so we have a plus e times e. And then the next step is in fact leftmost, because we're using this leftmost variable in order to get the b, and then the next step is trivial again, so that gives us a plus b times c. So this is a leftmost derivation. Now you can come up with rightmost derivations, which would give you other stuff, different derivations. The derivation tree basically doesn't differentiate between leftmost and rightmost. If you wanted a leftmost derivation, you go from e to e plus e, and then basically you do a left to right traversal of that derivation tree. And so you would have e goes to e plus e, which is this, and then you have that e goes to a, which is this, and then that e goes to e times e, which is this, and then this e goes to b, and then finally the last e goes to c. So if you do a left to right traversal of that derivation tree, then you will end up with a leftmost derivation. Now, I made some snarky comment about this being an evil grammar. So let's see why it is evil. This is a derivation. And a plus b times c. So we are ending up with the same string, except we have a very different kind of development. If we look at the derivation tree corresponding to this leftmost derivation, and again it is leftmost, here we do this, then we take that e and replace it by e plus e, and then we replace the first e by a, and then we replace that first e by b, and finally the last one is trivial. So the derivation tree for this is e goes to e times e, and then this goes to e plus e, and this is a and b and c. So this string a plus b times c is now obtained in a rather different way. A way in which, for all practical purposes, we are in fact required to essentially evaluate the e plus e, the a plus b first, and then take the a plus b and multiply it with c, which is of course very different from what we did with the first leftmost derivation, where we do the a and add it to the product of b times c. The string is the same, the derivations are very different, and the interpretation that you would do in a parser, for instance, in a compiler, would wreak havoc, because either one of these two derivations is valid within this grammar. And so if you were to write A plus B times C, then for all practical purposes, the compiler, if it were to use this grammar to generate your arithmetic expressions using plus and times, and of course, if you want subtraction and division, you can throw that in. It just makes it a little bit more complicated. Doesn't add any useful information. But what is important here is that this grammar basically treats this derivation tree as equal to that derivation tree. Either one of those two derivation trees are perfectly okay. Which means, of course, that yes, the string A plus B times C is obtained, is parsable, is generatable by that context-free grammar, but that context-free grammar is evil, because you don't really know which of those two derivation trees or which of those two leftmost derivations are going to be used, and that, of course, is very bad, because obviously you have numbers for A, B, and C. For most values of for A and B and C, you're going to get something different if you do the A plus B times C as opposed to the A plus B times C. So even though both of these derivation trees are entirely legitimate for that grammar, there are two different leftmost derivation trees, two different leftmost derivations, and two clearly different derivation trees for that same A plus B times C string. And that is what is known as an ambiguous grammar. And ambiguous grammars are basically evil. You certainly don't want to have anything to do with them in the context of, say, a parser, a compiler, because obviously if you were to use this grammar in a parser, in a compiler of some programming language, and most programming languages that I know will in fact have arithmetic expressions, and therefore in that case you're basically screwed, because the compiler could at random decide, well, today I'm going to use this one, but no, tomorrow is Tuesday, I'm going to use that one. You don't really want that. That's certainly not particularly helpful in the context of a compiler. And so ambiguous grammars are evil. You don't really want them. They're not particularly useful. They will only create headaches and don't really contribute anything particularly useful. So if you want to generate arithmetic expressions, you can do this. Now this looks much worse. I'm sorry, backwards. T plus E F times T. Well, in this case, it makes no difference. All right, let me finish. So this will do what you want, and it will do it unambiguously. It means that given a string, there is one derivation tree, there is one leftmost derivation for every string that is in the language. So now, if we look at the other case, E plus T and T, F, no, I'm sorry, T times F, or F and F, same thing, open, E closed, and ID. Well, it makes no difference whether you use this grammar or that grammar for the arithmetic expressions using plus and times. However, if you were to include division and subtraction, then there is going to be a difference between these two, because what are you going to do if you have this? You see, when you look at plus and times are associative. Subtraction and division are not associative. So if you do A minus B minus C, how do you interpret that? Do you interpret that as A minus B minus C, or do you interpret it as A minus B minus C? Which of those two do you prefer? I mean, they're fairly straightforward. In mathematics, it's clear that these two are not the same. If you say 1 minus 2 minus 3, what are you going to get? Well, in this, it's 1 minus 2 is minus 1, so this would be minus 4. And in this case, it's 1 minus 2 minus 3, so that would be 2. Most of us will probably not want to argue that minus 4 is equal to 2. So clearly this is not associative. And so what is the accepted interpretation of this? Well, in most cases, people will probably take this one, which means you would have to have this grammar. If you prefer that one, then you would have to have this grammar. So, anyway, this is a little excursion into arithmetic expressions. You can think a little bit about it. This is fairly straightforward and fairly practical. And now, what is going to happen if I have a grammar in Greibach normal form and I do a leftmost derivation? Well, in Greibach normal form, with a leftmost derivation, I start with the starting symbol and leftmost. And then you can easily verify that you're going to get a bunch of terminals. Remember our convention W is a string over the terminals. And then you have a bunch of variables. This is it in star. So there is 0 or more variables, grammar variables, that you obtain by having a leftmost derivation. So this is always going to be the same kind of thing. There is an initial portion that consists only of grammar terminals, followed by only grammar variables. And so eventually, of course, you're going to get the X, which is your terminals only. And so what that means is in leftmost derivation, so if you have, say, here is another grammar for arithmetic expressions, except of course now it is in prefix notation. So if you had, say, E goes to times EE, and then this is leftmost times plus EE, and that's very problem. Anybody? What's happening? Do you all hear that noise?
No, everything seems good here.
Okay, all right, then who knows? So we derive E goes to times EE, then that E, the initial first E, we go to plus EE, and of course we need the E that is left, and then we have times plus A EE, leftmost times plus A B E, and finally leftmost times plus A B C. So that then means we're going to do the A, the plus AB. So effectively what we're in order notation, this is of course prefix notation, but in order notation, this is what we would be getting. A plus B times C. That's times plus AB, which is A plus B, and then this stuff plus AB is multiplied with C. So in order notation, this would be that. And so as you can see, initially we have E, which means W is epsilon, and the gamma is just E. And then the next step is the W is star, and the gamma is 2 E's. And then the next step, the W is times plus, and the gamma is 3 E's. And then the next step, the W is times plus A, and the gamma is EE. And finally, the W is times plus AB, and the gamma is simply E. And the last step, then W is times plus ABC, and the gamma is epsilon. So now we don't have any variables, and that would be the string that we derive in this grammar, which does prefix arithmetic expressions. And it also has the advantage that this is in Greiberg normal form. And now we get to the question, how do we find pushed-out automaton that accepts by empty stack precisely the language generated by the context-free grammar. So we have a context-free grammar G, and then we go to G prime, which is in Greibach normal form. And now what we want to do is we basically want to take this gamma as the stuff on the stack, and the W is the stuff we've consumed. So initially we start with E, and then we get times EE. So now the stack is EE, and then we have 3 E's on top of the stack. Then we have 2 E's on top of the stack here, 1 E on top of the stack, and here the stack is empty because we've consumed every single times plus A, B, and C. And so in this case, what we're going to get is a push-down automaton, which has the terminals of the grammar. So G prime is in TPS, and it has those terminals as alphabet of input symbol. It has a single state. It has obviously a move function. It has Q as the initial state. There is only one. S is that S which is the starting symbol. And because we're accepting by empty stack, we don't need any final states. Okay, so this is that T. We have one state. This is that S, and we don't have any final states. Let's see, something is missing. Oh, I'm sorry. Forgot one thing. The stack symbols. The stack symbols are in. All right, then we have the move function, then we have Q and S and empty. So basically, yeah, forgot all about that. Of course, I was implicit in the explanation. Basically, this gamma is what our stack is all about. Okay, so obviously, if we have several grammar variables, in this case we have only one, but if we have several grammar variables, then obviously these are all going to be in N, and so N is the set of all stack symbols. So if we take this particular example, plus E, E, and times E, E, and ID, well, then for every production, A goes to little a gamma, we're going to put into delta of Q, that state, we have only one state, and the A and the little a, that will contain Q and gamma. That sort of looks complicated. It's actually not that hard. Let's do this example. So we have a single state. We have a single grammar variable. We have plus and times and ID. As you can see from this construction, this A is always a terminal. It can't be epsilon, because in a Greibach normal form grammar, every production starts with a terminal, and so this is obviously empty here. And then we have E. If we see E and we have a plus, then we're going to replace that E by two E's. If we see a times, we replace that E by two E's. If we have an ID, we replace that E by epsilon. And this is now the full push-down automaton for this Greibach normal form grammar. And if you, in general, if you had more than more variables, then let's look at another example. A, S, or A, and A goes to B, S, or A, B, B, S, or B goes to, no, that's not good. Let's do another B. C, or CS. So in this case, so this would be an example for that. And so in this case, we have again a single state. It's just, we need a state. We have S, A, and B. We have A, B, and C. Obviously epsilon, but epsilon doesn't do anything. And so we have S goes to AS, which means QS. That comes from this. Or AA, QAA. All right, then we have A goes to BS. So this is QS, comes from that, or A, B, B, B. So this is Q and B, B, B. And finally, B goes to C. So B goes to Q and epsilon, that's that. B goes to C, or QS. And everything else, there's nothing here, nothing here, 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 and epsilon is empty. So this would be the push-down automaton for this context-free grammar. And of course, the whole trick here is that all the heavy lifting occurs when we convert that given context-free grammar to a Greibach normal form grammar. Once we have a Greibach normal form grammar, the construction of the push-down automaton is completely trivial. You take a production, variable goes to single terminal followed by 0 or more variables in the grammar, and in that case you are going to take the Q is always in the grammar, in the push-down automaton, it's always going to be the same. That's just a formality. And so you basically have you look at the A, which is what is going to, is the left-hand side of the production, and the A is the starting terminal on the right-hand side of the production, and there's the gamma. And so this is these three productions give you this push-down automaton. Those 6 productions are going to give you this push-down automaton. Here you have, of course, only one variable grammar variable E. Here you have three grammar variables, E, S, A, and B, and that's how you get the push-down automaton. In both cases, you get a push-down automaton, and it essentially simulates that leftmost derivation where you're going to get the stack being populated by that gamma, and the W is what was already consumed. And finally, of course, presumably, if the word is generated, this X is generated over the terminals, then that means that the gamma is empty, which means your stack is going to be empty of that push-down automaton. So if we have, well, let's see, that was the grammar, the times plus ABC. So we have times plus ABC. So if we go through this, we have E, then we have times EE. So there is EE on the stack. And then we have that plus. So we start with this. So Q and times gives us two E's. So the stack at this point is, we start with that, and so we replace the E by two E's using this E top of, so we have this. This is the starting situation. The stack contains E, and then we see the times, and so the times then basically says we're going to replace that single E by two E's. So we now have E on top of the stack again, and then we have a plus, and that gives us another E, so that E on top of the stack is replaced by two E's, so we get this. And then we have an A, which is ID, which is means we're replacing the E by epsilon, so that gets popped. And then we see the B, that's another E that's eliminated, and then we see the C, that means that E is eliminated, and at this point the stack is empty. We've consumed the entire word, and that is how we have acceptance by empty stack in this push-down automaton. And you have a similar situation for the other example that we have here. Any questions? So that means at this point we have basically shown that given a context-free grammar G, we can construct a push-down automaton P that accepts that language, the language generated by that grammar, by empty stack. Does anybody want to go through the various slides so you can take pictures? Slide 1. Slide 2. Slide 3. Slide 4. Slide 5. And slide 6. Okay, so we will then continue with this on Wednesday. And we're going to go from push-down automaton to context-free grammar. I want to warn you, this is going to be the most ugly algorithm of this course. So, be warned. See you on Wednesday. Bye-bye.
Thank you, Professor.